Okay, hello everyone. So today we're going to do our start of chapter 8, looking at acid-base equilibrium. So a lot of this is going to be looking at concepts you already know from grade 11, reminding you of what Bronsted-Lowry acids and bases are, and then obviously starting to take a look at equilibrium's involvement here. Okay, so Bronsted-Lowry theory. So acids and bases, of course, are in solution. And a lot of the time we have reactions happening in solution. So remember that even though it may not be an acid-base reaction like what you're thinking of with hydrogen and hydroxide, just the fact that we have an acid interacting with water is also a reaction. So we have an acid-base reaction. So our water in this case is behaving like a base. So if you remember, a base is considered to be anything that accepts a proton. So what's happening here is this hydrogen is essentially being lost from HCl. So anything that loses a hydrogen ion is considered to be an acid, and anything that accepts a hydrogen ion is considered to be a base. So if you notice, our water has now become hydronium ions. So meaning we have water with that extra proton. So remember, what's moving here is a hydrogen ion, but that's also called a proton, because a hydrogen atom, once it loses an electron, it only has one proton. So technically this is water with a proton on it. So we have H3O plus hydronium. And what's left over here is a chlorine ion. So after the hydrogen has already left. So this right here is showing the process of a Bronsted-Lowry acid-base reaction. Okay, so don't worry, we're going to review all that concept again. So just a reminder of what hydronium looks like. So when acids ionize and react with water, it forms this H3O plus. So it's a polyatomic ion. Essentially, it's water with an extra proton, as I was mentioning, right? So a hydrogen ion with a positive 1 charge. So sometimes it's called a hydrated proton because really this is water, right? Anything with hydrate, right, means water. It's a water with a proton on it. And the reason why it forms the structure is this is a coordinate covalent bond. So meaning the original lone pair of electrons on the water is actually able to form a bond with the hydrogen ion. Okay, so you don't need to know not necessarily how to draw this Lewis structure, but more importantly, know like why is this being produced, right? So it's a hydrogen from the HCl reacting and forming with water. So sometimes your textbook does this a lot. Instead of writing out hydronium, it will write out H plus, AQ. So this automatically means whenever you see hydrogen ions in solution, it is the same thing as saying hydronium. So technically, hydrogen ions are always hydronium. Whenever hydrogen is in water, it will produce this. So you never see hydrogen on its own. We can use that as a symbol to represent hydronium, but I typically will write out hydronium itself so there's no confusion. Okay, so same thing can happen if you have a base. So if you remember from grade 11, NH3 is considered to be a weak base. So remember, the definition of a base is that it is going to accept a proton or a hydrogen ion. So in this case, it's interacting with water, and water is doing the giving away of our hydrogen ion, so water is considered to be an acid here. So the remnants left over is we have NH3 now becoming NH4 plus. So remember, this is NH3 with an extra hydrogen ion. And of course, once water removes a hydrogen, and just a reminder, sometimes we call water HOH to remember that when water breaks apart, and if you remember our organic chemistry, that happened quite a bit, whenever water breaks apart, it becomes H and OH. So that's why the leftover part here is actually an OH ion, right? So we have ammonium and hydroxide. Okay, so this is it again. So we're going to go over this. I know it's repetitive, but some of you may have, grade 11 was a long time ago. So the definition of an acid or base